This is Smarter Cars, a podcast about autonomous vehicles.
This is the finish line. The Stanford racing team has made its way into the history books.
But the most important thing for me is it actually doesn't matter who comes first. It matters that we as a community achieve it.
Early in a technology, 1,000 flowers should bloom.
Welcome to Smarter Cars. This is your host, Michelle Kairouz. In this episode, we talk with Tarin Ziyaee. He's a co-founder and director of AI at Voyage, which is making autonomous taxis. Tarin previously worked at Apple. He has a degree in electrical engineering from George Washington University and a master's in neuroscience from George Mason University. Tarin, welcome to the show.
Thank you.
So you are a co-founder and director of AI at Voyage. Tell us a little bit about what you guys are doing.
Yeah, thank you very much, Michelle. So at Voyage here, we're actually trying to pioneer making the best robotic taxis ever. This is, of course, in the self-driving car space. While we can't, exactly say, give too many details as far as like where we are right now, but we can say that we have deployed in California, that's our mission to bring about the onset of free robotic taxi rides. So
great, and so you guys are taking existing vehicles from an OEM, and you're creating a technology layer on top of that.
Yeah, that's right. Exactly. We're not building a car in a sense. We're not going to reinvent that particular wheel. We're definitely trying to make sure or use as much of the ecosystem as there is. And, one big part of the ecosystem is that there are cars out there that you can have a drive-by-wire kit attached to, So, we're not trying to make new hardware in that sense or new sensors or something like that. I think there are a lot of very interesting companies out there that do that. We'd be more than happy to start utilizing new sensors and new types of hardware as they come online. Mm-hmm. But we're not playing that particular game, no.
And so you're going to offer mobility as a service, basically, and be the distribution platform where you're actually providing service directly to the customer.
That's right.
Okay, great. And tell us about your role at Voyage and how you're building out your team.
Sure, Michelle. Yeah, so we just started recently. We're actually a spin-out from Udacity. We have a lot of DNA here. We have some people from Google. We have some people from Apple, including myself. From people from Waymo. We're trying to keep it lean and mean at the moment. Like right now over here, I'm the director of AI and algorithms. I'm also a co-founder. So I'm leading basically our efforts for all of autonomy and all the algorithms that go there. We have a fantastic team over here. I could not ask for anyone different as far as that goes. That's basically what we're trying to do now. At this particular point in time, we're looking actively for people involved in motion planning.
Great.
That's kind of like where we are at this point of the recording, but. This is definitely a very exciting time to be involved in this space.
Yeah, very exciting. So let's talk a little bit more broadly and help us understand some of the remaining engineering challenges for autonomous vehicles. And, I guess what we'll talk about today is really getting to level 4 or hopefully someday level 5 with a truly autonomous vehicle rather than some of the in-between phases like assisted driving. Can you help us understand what the different pieces are of the software that you need to develop to have an autonomous vehicle?
Sure, Michelle, sure. Yeah, so it's actually very interesting. I mean, so traditionally in self-driving, right? And I say traditionally in the very contorted use of the word, right? And it's a very new field, obviously, It's, self-driving right now, it's a very multidisciplinary field, right? So, it pulls in a lot of technologies and science from, controls and, perception and localization, mapping, motion planning, things like that, right? So these are kind of like our the traditional buckets, if you like, of how things fall within the self-driving paradigm, right? But that is not to say that this is the correct way to do it. It's a way to do it in a sense, certainly, right? To localize yourself, to have a map that you can localize to, then you can do some background subtraction maybe, then you can go and you can track objects, and then you can go do motion, like that is a way to do it. But the field is still, I would say, not that developed. It's still not that mature. We're taking a lot of, there's a lot of, inertia coming from, the computer vision community, the DARPA community, past DARPA challenges, things like that. So there's a lot of inheritance of a lot of these techniques. And people have kind of cobbled them together and tried to make them work and things like that. I think there's a lot of space for improvement there, right? We don't know exactly what the correct architecture is, and I say we as like the community, right? We don't exactly know that. I think that's kind of like the holy grail, right? Is like what architecture do you actually need in order to make this work, right? So that's one thing that I kind of see happen in almost a lot of self-driving companies, right? Is that they've sort of taken some architecture from somewhere, and they try to make it work in that sense, right? There's a lot of different ways in which we can imagine putting together a self-driving car. I don't think that we as a community have discovered the optimal way just yet. So there's definitely a lot of work to be done there.
That's a really interesting point, that the way it's been thought about in the past isn't necessarily the way it's going to end up.
That's right. Yeah, because you have a field like controls that's very mature, right? It's been very active since the 50s and 60s. You have like localization that from the turn of like this past century, I think has become quite mature. Mapping, same thing, right? Perception, though, is something that's really new still. We're seeing a lot of new waves happen in perception almost every day. That's usually synonymous with the deep learning revolution as well, right? That kind of took off, 2012,
right?
With AlexNet and things like that. So these different buckets are kind of, have different levels of maturity. We tend to kind of try to put them together in a sense to make something work, right?
Right.
I don't think, to my knowledge at least, I don't think anyone has sort of, sat down and said, hey, you know what? How should we actually do this for a product in a sense, right? How should these pieces actually fit in together, right? Do we need mapping? Why do you need mapping? Why do you need to localize? Is that something that we can actually do away with? What level of perception do you need, right? What level of perception do you not need, right? So there are all these little details there that I think tend to be lost on like a lot of people at large, especially in the zeal to field something, right?
Right.
But I think that in order for us to make a good product, we have to really kind of go back to basics and say, okay, how should we make, or what does a self-driving car actually need, right? Where are you deploying it? That matters in a sense, right? What can I kind of get away with in that sense, right? Do you need to solve AI to make self-driving? Probably not, right? You could do self-driving if you solved AI, right? But you probably don't need, to solve AI to do self-driving, right? So that's where it gets really interesting. What does that threshold look like? And I think that's, knowing that, having that maybe discipline and hygiene to kind of go and try to figure that out, I think will take us a long way.
Right. So what do you think is working well, and where do you think the most progress needs to be made, kind of along that continuum and across those buckets, as you point out, whether you think of them in individual components or not? What are the areas where you think the most work is needed, or some new approach might be needed to make progress toward successful autonomy? Sure.
Yeah. So the story, Michelle, kind of starts at the sensor level, right? The very first question is, okay, you want to make a product, right? For autonomous driving, right? What sensors do we need in a sense, right? Very naturally, it's easy to say, oh, hey, we need cameras, right? Because cameras are, give us the analog to what we see in a sense, right? Mm-hmm. The problem with that is that if you just kind of do cameras, you kind of, almost have to solve AI in a sense, because, to make sense, to infer everything about the world that's relevant to you as far as you move, moving through it, Mm-hmm. So immediately then you say, okay, well, maybe there's another sensor that can help me there. Maybe there's a sensor that gives me depth, like a LiDAR, right? LiDAR is actually really good at giving you, some semblance of a dense depth map in a sense, right? So automatically, that variable is not something that you have to infer anymore, right?
Right.
From like a bunch of images, you could infer depth, and there are many techniques for you to be able to do this. There's stereo techniques, there's techniques of deep learning, things like that, right? But that may not be the proper way to do that if you have a sensor that's already going to give you that for free. You see what I'm saying? So it kind of starts. So it kind of starts at the sensor level in a sense, right? Like what sensors do we have access to that say provide some measurement of the scene that's like important in a sense, right?
So having more sensors in different ways allows you to constrain the AI problem to make it more manageable?
You could say, yeah, exactly. I mean, the way I would say it is, having, being smart about, for example, what type of sensors we have. Let's just constrain the algorithms, if you like, right? The algorithms, so that we need not infer something that we can actually measure, right? And depth is a very good example of that, right? Like, if you can measure depth as far as like, the range of something, right? Why would you ever infer that from a series of images? You see what I'm saying?
Right.
And so, some arguments can be made of the fact that, well, what if your sensor fails? Like, for example, in rain, how is your LiDAR going to act? Okay, that's one thing. What if it's too expensive, right? That's another thing, But like fundamentally, we have to ask ourselves, okay, what sensors are we going to be using? Because that really colors the algorithms and therefore the AI techniques that you're going to end up using, right? If you're relegated to just images with a camera, if you force yourself to just use a camera and images, then you have a lot of work to do, right? You kind of then, that kind of pushes you a lot towards, you kind of have to make huge strides in understanding the world and AI at large, estimating depth of, having some representation of that, right? If you kind of say, okay, I'm not going to go down that route, if you have a sensor that gives you depth, all of a sudden you might have bypassed a lot of that hard work, right? At the cost of maybe it's a very expensive sensor and maybe it doesn't work in rain and things like that.
Right.
But, you kind of have this shortcut all of a sudden, say, okay, you know what, I'm not going to infer depth, I have that. What can I do now, right? So that there's a lot of detail at play here. I mean, just even like your starting point is really critical to where that takes you in a sense,
So if you have LiDAR and radar and cameras, are there any other sensors I'm missing there, or are those basically your inputs?
No, I think traditionally those are kind of inputs. Some people also use ultrasound to give you an active measurement of distance as well. So I think it's also there. It really comes down to there's like two types of ways to sense the world, right? Passive sensors, active sensors, right? So a passive sensor is something like a camera that just takes in light, right, with an optical spectrum, and it makes this image. An active sensor is something like a LiDAR, like a radar, like a sonar that will actually send some signal out into the world, get those reflections back, and then try to make sense of it in a sense, right? Different sensors, of course, will work on different physical principles, right? So with radar, for example, you could measure velocities or radial velocities if you like. LiDAR, you can't so much do that just yet. Sonar can also give you something like that, So there's different ways of measuring things in the world based on what sensor you have, right? I do have to say that there's been a lot of kind of like pulling back a little bit. If you zoom out a little bit, we've kind of been at the mercy of the ecosystem right now, because if you look at, like, for example, LiDAR or radar, who are those coming from? Those are coming from kind of established companies, Delphi, for example, Velodyne, people like that, who've kind of developed these within the driverless the driver assistance paradigm, right? So they kind of make this one unit and they integrate it and they go to an OEM and then there you have it, right? So that's kind of the first constraint, is that we're kind of dealing with sensors that were made with a specific purpose in mind, right? You might not get visibility into exactly what they're doing, how they're doing it, things like that. Because of that, a lot of people will gravitate to cameras because, camera is a much simpler device in that sense, but also because it's easy to associate computer vision with self-driving cars with AI. Whenever someone hears one of those three things, they think of the other two. It's kind of like this natural association in people's mind, right? So, there's a lot of this kind of association in people's minds, and people then think, okay, with a camera, what can I do? And they kind of start there, and they start looking at all these deep learning algorithms to process camera images, and that's great. But in the zeal of doing that, you might lose some really important granularity on, hey, was this actually the right approach for a product? That's kind of the risk there, right? You kind of just step back and say, okay, in order to make a self-driving car do X, Y, and Z in situation A, B, C for a product that's viable, what sensors do I need? And that will kind of dictate what algorithms you can bring to bear, and that will dictate whether or not you can actually make this happen.
And with all of those sensors, how are you looking at then the algorithms, for these various tasks that the car faces? How are you looking at these buckets in terms of where do you apply the deep learning, and how do you mix together these techniques?
Different buckets. Yeah. So deep learning, Michelle, this is definitely a very powerful technique. It's a very powerful, it is basically like the most powerful pattern recognition technique that we know of at the moment, right? Deep learning, right? So it's basically saying, hey, you know what? I want to essentially learn this hierarchical decomposition of the world. I'm going to learn the specific features of different layers, of different levels of the hierarchy. I want to put them together in a certain way, and it's going to give me some answer, right? Very, very powerful. I think what we need, though, is to know where you might need to use this in an architecture, right? So going back to the fact of, do not infer that which you can measure. Let's say this is the first maxim, let's say, right?
Right.
If you have that at the back of our mind, right, then we can say, hey, you know what? If I already have depth, I should not try to finesse that from an image, right? There might be some cases where we need to do that, sure. But at first glance, I probably shouldn't do that. I already have a sensor to do that, right? Second thing is that, and this is something that I think is quite endemic, is that you don't need to classify the world in order to not bump into it. Okay?
Explain that for us.
Yeah. Yeah. I mean, so if I put you on a strange planet like right now, right? Mm-hmm. You might not know what things around you are. You might have some weird alien plants and weird looking, rocks or something, or some terrain or some weird object, right? You don't know what they are. If I say, hey, Michelle, what is that? You say, I have no idea. It's some weird purple thing out there, right? That you've never seen before, right? But you would know to avoid it. You would know how to navigate your way around that, right? If it started moving, you would know how to get out of its way, for example, right? So what's going on here is that you never need to classify, right? As a human, I can avoid things in the scene without me knowing what they are, right? It's nice to know what they are. It's useful, but fundamentally, I don't need to know what something is in order to avoid it. You see what I'm saying, right?
Yeah,
I mean, I come across stuff, if you go hiking, right, you'll come across things that you might not recognize what they are, but you know where they are. You know that it occupies a certain amount of space vis-a-vis you. Mm-hmm. And because of that, because you have a good spatiotemporal reasoning, you know that this is what you should do to avoid bumping into it, right? So this is the first thing. This is where it's important to have some, how should we say, say algorithm hygiene, right? Is a sense of, before I even need to classify anything, what we really need to do is learn about how the world evolves in a temporal aspect. What is how do we do spatio-temporal reasoning on the world, right? After that, it's useful to know, oh yeah, this is a piece of grass, this is a car, this is a person, this is a cat, right? But I don't need that to avoid them. What I really need is a way for the machine to understand spatio-temporal reasoning, which is just a fancy way of saying it should know about how the world evolves over time, such that it doesn't bump into stuff due to its own motion, and vice versa, right? That is one of the, I would say, very important subtleties, and one of the very important subtleties that we should be very, very well aware of. People would be very, very smart if they're aware of that, basically, right? And they use that to guide their algorithm design.
What about prediction? What about this idea of sometimes I think you want to know what the object is because you're trying to predict what's going to happen next and where it is going to go, et cetera. So how do you feel about that? And
Sure. Yeah, sure. I mean, so it's like this, right? The whole thing looks like an onion, right? I mean, fundamentally, right? Fundamentally, you don't know, you don't need to know what things are to, let's say, not bump into them, right? Fundamentally. It certainly helps, though, right? It certainly helps to say, hey, you know what? This is actually an elephant, right? And because it's an elephant, it's going to act in a certain way because that's what elephants do, or this is what elephants are capable of doing and not capable of doing, right? And that, I mean, absolutely, that helps you predict, where they're going to be over time vis-a-vis you, right? So classification definitely helps you predict the world in a spatio-temporal way, but you should not depend on that. You see what I'm saying? There's a little subtlety there, right? Is that it can certainly help make your predictions better, but you don't need, and neither should you depend on that, right? Fundamentally, in order to understand how the world evolves over time, so that you can predict. This is where this is a very important, I think, subtlety to point out. Absolutely.
Yeah. So using your sort of more restrained view of the software, how do you see what comes next in terms of, are there going to be additional breakthroughs? Do we need additional breakthroughs in the technology in order to get to a level of comfort where we can deploy autonomous vehicles? Or can we take the existing technology and algorithms and things we have today and just improve them by additional data sets and miles driven and simulations?
Right.
Is there kind of a fundamental breakthrough we still need? People talk about unsupervised learning and other aspects. How do you see it?
Sure. It's actually a very good question, Michelle. So here's where I see it, right? I think basically there's a couple of things going on here. Number one, it depends on the application area. What do I mean by that? In self-driving cars, right? I think they're going to be fielded and deployed like cell phone towers and cell phone service was kind of deployed in say the 90s, and that it's kind of like patchy spatially in the beginning, right? You only had service in one location, then another, and over time. Now, 30 years later, we kind of have global coverage in a sense. And even then you have some pockets where you don't have service, right? So okay, that's the first thing. Second thing is that because of that, right, you might be able to solve, quote unquote, solve autonomy or autonomous driving for specific places first. And then from there, based on what you learn about the shortcomings and things like that, you could say, oh, okay, you know what? It would be nice if we had a breakthrough here, here, and here. You see what I'm saying? And that's my expectation for how this thing is going to evolve, right? Going back to your first question of, do we have everything we kind of need right now to do autonomous driving, right? Frankly speaking, I don't think anyone knows just yet, because I don't think anyone has really been that hygienic, to be honest. It's like I said, people just have kind of just, in their zeal for getting something working, have kind of rushed to put something out there and cobble something together. We kind of have enough tools out there so that you can put stuff together very quickly and make something work as a demo, right? But as a solution, I think no one's kind of done like their homework in a sense, to say, hey, you know what, given all these technologies that we have, what combination of them can we currently leverage to do self-driving in this area, right? That is kind of like one of the first questions, right? My gut feeling here is that we actually do have a lot of techniques and technologies right now that would allow us to field and deploy as a product self-driving technologies in some areas, right? As far as maybe one, if you like, one sort of thing I would like to have on say the wish list is having the machine be able to do this spatio-temporal reasoning, this prediction, in a sense, to be able to learn it in a very elegant way, in a good way, I think is going to be very crucial. However, even with that, I think you can, I think you can kind of get away with, again, depending on the scenario, okay, where you deploy, I think you can get away with something more traditional in that sense, right? So that's kind of how that's kind of my feeling of the space in that regard, right? In the sense of, do we have a lot of technologies out there that are very useful? Absolutely. Do we know the optimal way to combine them? I don't think so. I don't think anyone has done their homework there just yet. I think that there is going to be a good way to combine them to enable self-driving in some scenarios, right? And I do think that if there was to be maybe one, fantastic breakthrough that I would wish we had right now, it would be, is there a good way for us to teach machines about spatio-temporal reasoning in the world, right? The kind of the physics of the world in a sense, right? Can we teach them the physics of the world? Can we teach them how to predict how the world evolves, kinematically even, right? That I think would be something that would lead to a huge breakthrough in self-driving, yes. That said, I don't think it stops us from deploying self-driving in some scenarios.
Right.
Yeah.
So, talking about getting to deployment, let's talk for just a minute about safety and this idea of how will we know that the cars are safe enough to deploy. And I think when we see policy discussions around this, we see perhaps talking about an operational design domain and companies needing to sort of certify that for this operational design domain in this area, here's what the car is, the car is good to go. How do you think about the kinds of testing, the amount of miles, or the types of testing you would do in order to get comfortable yourself that a car was ready for deployment? Sure.
Definitely. So yeah, and people forget this, but yeah, I mean, anyone working on self-driving cars is making machines that have the capacity to kill, right? So it's a very, very important question, obviously, right? So what I would do there, Michelle, is actually, is basically the following. I would essentially decompose the problem, right, into where things can fail, right? So for example, the first question I would ask is, hey, when or how often does my sensor fail, right? What are the failure cases of, say you're using a LiDAR, right? What are the failure cases of your LiDAR, right? Well, maybe it doesn't reflect off some materials. Okay, that's one thing. That's a huge thing, right? In what way can the LiDAR fail, right? This is a very hardware-esque question in that sense, right? What happens when and if the LiDAR gets covered by something, temporarily or permanently, let's say, right? Do you have algorithms that can detect that state in a sense, right? It starts again from how you sense the world, right? What is a failure? When do your eyes fail? Is maybe the first question that we might ask of a human, right? When does the eye fail? Well, when the sun's in your face, things like that, right? Okay. After that, once you have that, I would say, okay, based on the algorithm that I'm doing, and really it's really dependent on the algorithm that you're kind of doing, right? What are the failure cases of this particular algorithm, right? Well, I'm taking in data like this, and I'm processing it like that. I'm doing this, and I'm assuming this, and this, and I'm doing it. That can kind of, let us, kick in the tires for that particular algorithm knowing how the algorithm is working allows you to kick the tires there, right? You can kind of do some testing over there, right? You can enumerate the failure cases of some particular algorithm given the data that it's going to expect, things like that, right? And you kind of keep doing this, along the chain. Once you have that, and once you've kind of solidified each module in that sense, Michelle, right? Then you can start talking about, okay, global statistics. Like, okay, we're now sure about how the sensor fails. We know the failure cases. We know what these algorithms are doing. We know how they're going to fail, how they're not going to fail, things like that. After that, then I think it's just a matter of fielding it and collecting data and, basically doing, basically getting the statistics of how this thing performs in the real world, right? Mm-hmm. And then coming up with some acceptable number. And then, at the end of the day, there is going to be some statistic of failure. Are we as a society going to be okay with that? There is some statistic of failure of, for example, flying, right? Right. We accept that as a society. Every time we get on a plane, we say, hey, this thing might just come crashing down. Or at least, this is the expectation, not expectation, of course, but, it's something in the back of, It's a possibility. Same thing when you go to drive. When you go to drive, you say, I might get in a car accident today, right? Because of something out of my control. So, there's kind of like this maybe the question to ask ourselves is, what is the acceptable threshold for, safety in autonomous driving? And then you can maybe work your way backwards from there in a sense, right? But as far as the how would you test that? Yeah, I think it's a matter of, just doing chain testing like everything else. When does this module fail? When does this module fail in conjunction with other modules? And just going off that, really. So.
How do you feel about some of the end-to-end network approach where, it's really sensor input in and driving tasks out and, realizing that no one's really made this work, at any acceptable level yet. But if you got to a place where that was an approach being considered, what about the black box, kind of the lack of interpretability? How do you feel about testing that kind of a system? Like, how would you do that?
Sure. Yeah. So this is a very specific question, Michelle, about one particular algorithm, let's say, right? So, saying, hey, here's one algorithm, how would you test it in a sense, right? Mm-hmm. So, like any algorithm, you need tools for you to know what it's doing, right? What is the internal representation that it's coming up with? Why is it coming up with that, right? How can that representation fail? When does it fail, right? So all kind of the due diligence you might do for any other algorithm comes into play here as well, right? Mm-hmm. The fact that we might not at this point in time know how exactly to probe the inner workings of some hierarchical deep net, that's one thing. That just tells me that we don't have the tools for that yet, right? And because we don't have the tools for that yet, it might be hard to assess when this thing might fail, when it might not. You see what I'm saying? It's the same thing for any other algorithm, right? Mm. And so that would be my first reaction as far as that goes. Now, as far as whether or not this algorithm is useful or useless, I mean that, I try not to be dogmatic about that. I try to keep an open mind as far as different algorithms. We just need to have enough, maybe maturity or hygiene to say, okay, here's an algorithm, great. Can I probe it? Yes, no. How do I probe it? Do I have the tools to probe it? What are its failure cases? What are its, cases where it doesn't fail? Things like that. Once you kind of have a good feel for that, then you can kind of move on from that. Right? But if I was to just give you a black box, any black box, it's not magical to deep nets. If I just give you any black box, you would rightfully so say, well, what is this thing doing exactly, right? Mm-hmm. How do I probe its failure cases? How do I do that, right? And so, there are two ways for anyone to probe a function or a black box, right? You can via knowing what it's doing, try to predict how to make it fail, right? Or if you don't know what it's doing, you can just do these statistical tests and put it through the ringer and see when it fails. But I think we need to have both of these techniques in order to feel comfortable about something as safety critical as self-driving cars, right? And I think the challenge right now with some algorithms out there is that we don't necessarily have the appropriate tools in order to properly finesse what an algorithm is doing. And it's not a criticism of the algorithm. I think they're very powerful. I just think that the tools haven't caught up just yet. And so once that happens, I think it'll be a different question in that sense. Then it becomes a question of, okay, where and how and should I even use this particular algorithm like any other algorithm, right? So that's how I would think about that.
And everybody loves to play this game, so I have to ask the question because everybody does. When do you think you would expect to see? I can't not ask it. When would you expect to see in an urban setting autonomous vehicles deployed in a ride?
Oh my God! Yeah, no, Michelle. Yeah, you had to ask that question, of course. It wouldn't be an interview without that question, right?
Right. I know what you're going to tell me. 1 to 20 years. 1
to 2,000 years. No, nothing that large. No, I mean, this is this is actually a very hard question, Michelle. I mean, so and I hate to, give you this answer, but it really just depends. It really, really just depends, right? From a technology standpoint, okay, from a purely technology standpoint, I think that we will have the technology necessary to deploy some types of self-driving cars in some types of scenarios within a decade, okay? That's purely from a technology standpoint. If you want to then throw in things like, the legal aspect around that and the safety aspect around that, that might add some more time to that in that sense, right? Mm-hmm. The supporting infrastructure, if we even need that, right? That's going to come into play, So, it's really hard. I mean, you have so many variables there, Michelle. You have the state of sensors, the expensive sensors, right? How quickly can you manufacture them? How much can you manufacture? What is the price point for them? And that's just for the sensors, right? What sensors do you have? What sensors are you at the mercy of, right? That's even before even talking about the algorithms themselves, right? Once you've kind of covered that, and I mean, the sensor hardware space right now is actually very exciting. There are many startups in the LiDAR space. There are a lot of startups right now that are trying to fuse different sensors together, different modalities together at the sensor level, at the hardware level,
And that could make some big changes then.
That's, I mean, of course, that's going to make, huge changes, Michelle. Yeah, humongous changes, right? I mean, just talk about like a LiDAR. If you have a LiDAR that gives you different frame rates, very fast frame rates, update rates, that maybe they're throwing RGB with that as well. And some other facets. I mean, that's kind of a game changer in that sense, right? Because it unlocks the ability to do different scenarios, right? So that's a very liquid phase right now in sensor technology, right? So that's one big variable, right? I mean, we might as well ask, let's ask ourselves, instead of asking ourselves when we see autonomous cars, let's ask ourselves, what is the state of autonomous sensors or sensors for autonomous cars right now? Right. Let's start there. I think that's in flux, like a lot right now. I think that within the next 5 years, if not more, we're going to see a lot of interesting sensors come online for this purpose, right? Okay, well, if that's the case, that's kind of going to change the way that we process data, because we have different data. We have, we can access it in a different way now. They're measuring different things together, right? So that opens up new possibilities, right? So this is why I kind of give a large, I'm saying like, a decade very roughly, just because it really just depends on the sensors. It depends on where you're deploying. It depends on the speed at which you're deploying, which the car is moving. There are all these different, depends on the scenario, right? Who you're serving, right? So, I mean, let's just say like this. I think that there's no going back. You can safely say that, right?
Right.
There's a huge ecosystem right now, that has everything from, hey, let's make you a great sensor, to, hey, let me label your data, to, hey, let me do, so there's no going back from that.
Yeah.
We also need to be aware of, where are we going to deploy, Are you just doing highways? Are you doing cities? Are you doing some other off road? I don't know. What does that look like, right? So there's a lot of variables at play here, Michelle. There's so many. It's, to be honest with you, I would say quite hard, very hard to predict, honestly. But what I can safely say is that there's no going back.
Yeah.
That's the most honest answer I can give you.
Yeah. It's a lot of moving pieces, and as you're pointing out, they all affect each other. Yeah.
That's right, exactly. Very tightly coupled. Absolutely.
Yeah. Great. Well, thanks so much for coming on the show today, Tarin. I really appreciate it.
Definitely, Michelle. Likewise.
All right.
Yeah. Thank you very much. Thank you very much for having me.
Thanks again to Tarin for coming on the show. You can find links about Tarin and about Voyage on our Medium publication called Smarter Cars. Thanks again for listening. We'll see you next time.